All right, so we've done a lot in terms of trigonometric functions up to this point. We've done work with triangles using law of sines, law of cosines. We've been able to find trig values anywhere, no matter which quadrant it's in, using reference angles. And now we're going to move on to graphing trig functions. So a couple of things before we get into graphing them, but we will be graphing all 6 trigonometric functions, so sine, cosine, tangent, cosecant, secant, cotangent. We're going to graph all 6 of them today. So before we get into those graphs, a couple of things for introduction. So first, all trig functions have what we call sinusoidal graphs, and they are going to be either even or odd. So even functions, if you were to plug the negative x value, would be equal to the same thing as if you were plugging in the x value. Now what this means is that the graph is going to have symmetry with respect to the y-axis, right? So if the y value is the same at x and at negative x, that must mean that they're symmetric across the y-axis. Okay, and then if they are odd, an odd function means that if you plug in the negative value of x, the value that you end up getting is the exact opposite of if you were to plug in x. So for example, if I plug in negative 2 instead of 2, and f of 2 is equal to 1, then f of negative 2 is going to equal negative 1. It's the exact opposite. What this results in is a graph that has symmetry with respect to the origin. So not with respect to another axis. The reason it's not another axis, well, we've already had the y-axis. If it were an even function, it can't be symmetric with respect to the x-axis because why? Because then it wouldn't be a function, right? If there were symmetry with respect to the x-axis, that means it's reflected across the x-axis, and that would mean that you have 2 y values for the same x value. So there's no symmetry with respect to the x-axis when we're talking about functions. Okay, so not all functions are going to be even or odd, but all trigonometric functions are going to be even or odd. Another characteristic of trig functions are that they are periodic, which means that they repeat. So rather than having just one large thing like a quadratic function is just one parabola, a trig function is going to have one shape that continues to repeat over and over and over again. So now for us, the way we're going to go about coming up with these graphs is we're going to use what we already know about the trig functions and the angles on the unit circle. All right, let's start with the sine function. So over here on the left, we have a table. Now I've only included some values here. You can absolutely put in other values that you know, for example, pi over 6, pi over 4, pi over 3. You know all those values, and that can help you come up with the graph. So sine of 0 is 0, sine of pi over 2 is 1, sine of pi, 0, sine of 3 pi over 2, negative 1, and sine of 2 pi, back to 0. Now over here on the right where the graph is, now that we know what values we're working with, we can go ahead and label. So on the x-axis, or t, we know we need 0, we need pi, we need 2 pi. Pi over 2 is going to be halfway between 0 and pi. 3 pi over 2 is halfway between pi and 2 pi. And then it looks like our y values will go up to 1 and down to negative 1. Now you'll remember that when we were coming up with solutions of sine and for cosine functions, if your c value was outside of negative 1 and 1, there was no solution, right? So that's also a good indicator that we don't need to go past 1 and negative 1 here. Now if it's helpful, you can absolutely use pi over 6, pi over 4, pi over 3, and use 1/2, root 2 over 2, root 3 over 2, get an estimate to get where those points will be approximately to help you come up with the shape of this graph. Okay, so using those points and using 1/2, root 2 over 2, root 3 over 2, we can come up with the graph of our function, and it looks like this. Now you'll notice that on either end of the graph, I've put a tiny little arrow just to help us remember that it doesn't stop at 2 pi or negative 2 pi, it continues. But it continues and it just repeats this same shape over and over again. Okay, so the domain of this function, negative infinity to infinity, the range, negative 1 to 1, inclusive. The period, so when we talk about the period, we mean what is the length of one unit that's repeating, the smallest unit that's repeating. So here you can see it when it starts at 0, it goes all the way to 2 pi, and then at 2 pi it's going to start that shape up again. So the period is 2 pi. And then lastly, is it even or odd? So remember I said that all of these functions are going to be one or the other. We can tell that there's no symmetry with respect to the y-axis, but there is symmetry with respect to the origin. So if you take any point on the graph, if you were to reflect it over the origin, you would end up with a point on the other side that is also on the graph. All right, let's continue. We're going to go through all of these functions. So we have 1 down, 5 to go. So graph of the cosine function. So we'll do the same thing, write down, fill out this table, come up with our graph, and then write down the domain, range, period, and whether it's even or odd. All right, so cosine of 0 is 1, cosine pi over 2 is 0, cosine of pi negative 1, cosine 3 pi over 2 0, and cosine of 2 pi back to 1. All right, label the graph here. And again, similar to sine, it only goes up to 1 and down to negative 1. All right, and again, you can use root 3 over 2, root 2 over 2, and 1/2 for pi over 6, pi over 4, pi over 3 to help you come up with the rest of the points as well. All right, so here's our graph. It looks in some ways similar to the sine function, but in some ways not. Again, notice that at the ends I've put little arrows to indicate that it continues. Note that it doesn't continue up straight. It would curve back down right at 2 pi. All right, so the domain, negative infinity to infinity. The range, from negative 1 to 1 inclusive. The period, so again, the period is what is the length of one cycle. So if you start at the origin there, right, you move across towards the right, you can see that once you get to 2 pi, it'll start repeating again. So again, the period for this is 2 pi. And then this one does have symmetry with respect to the y-axis. So this is an even function. All right, next we have the tangent function. This one is a little bit different. Sine and cosine are related to each other. There are things that are similar about those two. Now the tangent function, let's go ahead and fill out the table. So tan of 0 is 0. Now tan of pi over 2 ends up being what? Undefined. Tangent of pi is 0. Tangent 3 pi over 2, undefined. And tangent of 2 pi back to 0. Now not a lot to work off of here, so I definitely encourage you to use other values that you also know to come up with this graph. And we'll go ahead and label our axes here. Now for this one, you can label this going from 1 to negative 1. It's not completely necessary, just because we actually can go further than 1 and negative 1, right? Remember those restrictions were only on sine and cosine when we were finding solutions to trig functions. All right, so the domain, well, actually, let's draw out the graph. So all these places where it's undefined, we're going to draw in these vertical asymptotes. And then we know we have points at 0, at the origin, at pi, and at 2 pi. So here's what this graph looks like. Okay, it kind of looks like a cubic function. You know that it's not, because cubic functions don't have vertical asymptotes on either side, but the curve of the function, particularly in the middle, looks very much like one. So you can use that to help you remember. Okay, so the domain is everything except for all those vertical asymptotes. Now we see the vertical asymptotes are at pi over 2, 3 pi over 2, next one would be at 5 pi over 2. So you'll notice the pattern is that it's all real numbers except for odd multiples of pi over 2. All right, the range is from negative infinity to infinity, so no restrictions there. The period of the function, so what is the length of one unit of one cycle? So in this particular case, it looks like it goes from one vertical asymptote to the next vertical asymptote, and then it starts repeating. So really you're looking at what is the distance between vertical asymptotes. In this case, that would be pi. All right, is this function even or odd? Looking for symmetry. No symmetry with respect to the y-axis, but there is symmetry with respect to the origin. So this is going to be an odd function. All right, we have 3 more to go. Next, we're going to work with the cosecant function. You'll remember the cosecant function is the reciprocal of sine. So we're actually going to use that to help us come up with our graphs. So cosecant of 0 is undefined. Cosecant of pi over 2 is 1. Cosecant of pi, undefined. 3 pi over 2 is negative 1. And cosecant of 2 pi is undefined. Okay. So now, in order to help us graph, I'm going to very lightly draw in the sine function. You can make it a dotted line or put it in a different color. And what I'm going to do after I've drawn that in is anywhere that the sine function crosses the x-axis, I'm going to go ahead and draw in a vertical asymptote. The reason for this is because the cosecant function is the reciprocal of sine. So wherever the sine function hits 0, if you were to take the reciprocal of that, you'd end up with 0 in the denominator, gives you the undefined. So now we know that that's where all your vertical asymptotes will be for the cosecant function. All right, so now we can draw in our cosecant function. They're going to look like parabolas. Again, remember, I'm just relating it to a shape that you already know, but know that they are not actually parabolas. But they have sort of that shape, but they are restricted by vertical asymptotes, whereas parabolas are not. Okay, and this hopefully makes it a little easier to remember if you can relate it to sine, and remember in relation to sine what the function looks like. All right, so the domain of this function is going to be all real numbers, except for what? Wherever the vertical asymptotes are, you'll notice they're at pi, at 2 pi, next one will be at 3 pi, so it's all real numbers except for multiples of pi. All right, now the range. Now notice in this, there's a missing section from -1 to 1. So the range is from negative infinity all the way up to -1, and then from 1 all the way to infinity. Now the period of this function is going to be very similar to the sine function. The period is 2 pi, so it repeats every 2 pi. And then, is it even or odd? Well, this looks like we have symmetry with respect to the origin, so this is going to be an odd function. All right, we have two more left to go. So the secant function, this is going to be pretty similar to relating sine with cosecant. Now we're going to relate secant with cosine. So filling out our table here, we have it going from 1 to undefined to -1 to undefined to 1. We'll go ahead and label our graph. And again, we're going to draw in the cosine function to help us come up with the secant function. So here's the cosine function. Again, draw it in very lightly or draw it in a different color. And then again, we'll do the same thing. We'll draw in the vertical asymptotes anywhere cosine crosses the x-axis. Once you have that, then we'll do the same thing as with the cosecant function and draw in our what looks like parabolas, and that's your secant function. All right, so the domain is going to be all real numbers except for odd multiples of pi over 2. That's where we have vertical asymptotes. We have the range going from -infinity to -1, and then 1 to infinity. Again, notice that in between there's a gap, so we are excluding the numbers between -1 and 1. The period is the same as the period for the cosine function, which is 2 pi. And then the secant function does have symmetry with respect to the y-axis, so this is an even function. All right, we have one more, the cotangent function. And the cotangent function is the reciprocal of tangent. We'll fill out this table. So cotangent is undefined at 0. It is 0 at pi over 2, and so on. We'll go ahead and label our graph. And then anywhere that we see that our cotangent function is undefined, we are going to draw in vertical asymptotes. So at 0, at pi, at 2 pi, and so on. And this one, it does relate back to the tangent function because it is the reciprocal of the tangent function. And so this has, in some respects, a similar shape to the function compared to the tangent function, but also slightly different. So it looks a little bit like a cubic function. However, think of it as being reversed. Now the reason that happens is because it is the reciprocal function. So for example, if it's equal to 1/2 for the tangent function, the reciprocal would end up being 2. So that creates that shape for our function. All right, so now let's go ahead and fill in the rest. So the domain is everything except for the vertical asymptotes, which are at 2 pi, 2 pi, 3 pi, so on. So all reals except multiples of pi. The range, well, here the range could be anything, right? From -infinity all the way to infinity. And then the period, you're looking at the vertical asymptotes and saying, okay, well, the length of the cycle is going to be the distance between one vertical asymptote to the next. So looking at this, we see that's equal to pi. And then lastly, we have symmetry with respect to the origin, right? No symmetry with respect to the y-axis, which must mean that this has got to be an odd function.